about someone else.
Man, you're on thin ice.
Are we ready?
Introduce yourself.
Okay. Hello, everyone. Welcome to yet another graduate student seminar. And today we have me talking about the probabilistic method. So yeah, without much further ado, we'll hand it to the speaker. Hi. Welcome. Thanks for having me. So as a disclaimer, if you see me up here giving a talk, for the most part, it's because the planned talk for the week didn't go as planned. So.
As you look straight at me, yeah.
No. I didn't even tell you, so it's actually kind of my fault. So as such, there was also for a while people were like saying someone should do like a series on the probabilistic method. And so it was supposed to be me and my buddy, someone else that was also supposed to do it, but things didn't pan out. So I decided we're going to put the two concepts together, and now every time a talk doesn't go as planned, I'll show up and do a part of my probabilistic method series. So that's how it's going to work. The probabilistic method, in essence, this dude, Paul Erdős, made it very famous in the mid-20th century. Although people credit him for having invented it, but it's been used before. And in essence, it's a counting argument, right? So you have sort of a space, you have a set of objects, and you want to prove that a certain object exists in your space. And you want to do it specifically by looking at all the objects that you don't want and saying those objects don't cover the entire space. There's something else out there, and so it must be the thing that you want. And it's very specifically, it's especially useful in solving sorts of like needle in the haystack kind of problems, or if you will, like a hay in a needle stack kind of problems. Because well, like if you're given like a stack of hay and there's a needle inside, and then for some reason, I don't know, your vision isn't perfect, so you can't tell the difference. They all look the same. A way to single out the needle is just to use a magnet. You can use a magnet, wave it around until the needle sticks to it, right? And what are you laughing at? I'm trying to go somewhere with this. The needle sticks to it, and you're like, okay, well, this thing stuck to the magnet. It can't be hay. It's got to be a needle. But in general, if the object that you're trying to identify is already easy to measure, get information about, construct an example of, then you wouldn't use the probabilistic method. In general, say you're given a box of needles and there's hay inside. Now it's hard to single out the hay. But what you can do is do the same thing. Use the magnet, pull out all the needles, and you say, well, that thing didn't stick to the magnet, so it's got to be hay, right? So you're singling it out in the other way. You're pulling out everything that you don't want. In general, I guess you would say, or not in general, in this case, you would say the total number of objects minus, let's say, the number of needles, equals the amount of hay. So as long as this quantity is positive, I know that this quantity is positive. That's essentially all it is, the probabilistic method. So thanks for coming to my talk. No, so, and the one thing that you do extra is you divide everything by the total number of objects. That way everything becomes a probability. This becomes 1. This becomes something less than 1. This becomes something less than 1. And so you can use your probability axioms and everything that you know, and the numbers that you use aren't going to blow up. So as long as this is less than 1, you know that there's hay in the stack, in your needle stack. So this, I think, concept is very much, or before, maybe I should say this. There's a couple things that I'm going to be using to pulling for my sources for this series. And the notes that I'm using right now, it's called the Probabilistic Method by Michael Malloy, my boy Malloy, which I might change at some point, but it's a really good reference point if you catch the bug and check it out. Another great reference is, again, the probabilistic method. They're all basic names. And this time it's by Spencer, Joel Spencer. So this is what I'm going to be going based off. Everything I say and do is mostly going to be from, for now, from this notes, even chronologically. So, right. As a motivating example, I'm going to talk about a specific problem that we've already covered in the graduate seminar. Which is the girth of a graph and chromatic number problem, which we Boyun covered a long time ago. It's a great example of where the thing that you identify is hard to construct. It's the hay, and so you, well, the way she did construct it. But we'll talk about that. This is a little bit more than what was done last time because, well, we'll revisit what was said. So everyone knows what a graph is. It's a collection of vertices with edges inside and between. The girth of a graph, I'll write this here. Given graph G, okay. The girth of a graph is the length of the shortest cycle. So a cycle is just anything that looks like this, so on and so forth. Just a sequence of vertices such that it loops back on itself, and there are no repeated vertices, so these two can't be the same vertex. And you take all the cycles that your graph has, and you look at the smallest one, and the length of that cycle, meaning the number of edges it has, which coincides with the number of vertices it has, is the girth of the graph, and the chromatic number is the minimum k such that G is k properly colored. So so the minimum number of colors that you need such that your graph can be properly colored by those colors. And just to remind ourselves what that means, let's say we have a graph. What does proper coloring mean? Okay, I guess this is enough. So this is our graph. A proper coloring is an assignment of a color to each vertex such that if two vertices are adjacent, then those two vertices don't share the same color. Right? So if I color this vertex blue, I can't color any of these guys blue. They have to have a different color. But I can color all of them red because none of them are adjacent to themselves within each other. So, and that would be a proper coloring. So you look at the minimum number of colors that you need to properly color a graph. Essentially, how colorful the graph is, or how beautiful the graph is. And the problem that was tackled last time, well, before that, let's look at an observation. Let's say that a graph has no cycles, so it's acyclic. Then I can do this little algorithm, so I can do here. I can pick a vertex at random. I can just pick one vertex from the graph, and then I can look at all of its neighbors. Okay, whatever. And then I could take one of the neighbors, look at all of its neighbors, and do the same thing for the other neighbor, the other one, for all of them, and then do it again. So I can play this game, and my claim is that, my claim is that I won't have any repeated vertices when I do this process. Right, meaning this vertex won't be the same as like this vertex. And it's obvious why, because my graph is acyclic, right? So if these are the same vertices, I could just draw it like this, and there's a cycle. 1, 2, 3 of length, in this case 3, I guess 4. So this can't happen. But I'm starting with a finite graph, so finite number of vertices. So at some point this is going to terminate, this process is going to terminate, and the very last layer is not going to have any more neighbors to go up with. And if I'm done, if all the vertices in my graph is covered, then I'm done. I've drawn the entire graph. If not, then I do the same process. I take one of the vertices that I haven't already picked yet, or I haven't covered using this process, do the same thing. And by the same logic, these guys should turn out to be more and more trees. These are called trees just because they look like trees. And this is an exhaustive process to write down draw the entire graph, as long as it's acyclic, into trees. So now it's clear that the chromatic number of an acyclic graph should be, well, at most 2, right? Because what I can do is I can take each of these layers and give them a single color, and this is where the extra marker comes in. I can give this one the blue color. The next layer I can give black. The next layer I give blue, black again, and I do this for all of my trees. Then none of the adjacent vertices are colored the same. So the chromatic number should be 2. That's one observation. It's an important observation. It kind of alludes to something. So another observation we could see, maybe if the graph has triangles. So if the graph does contain a cycle of size 3, length 3, then if I try to color this vertex blue, I can't color these two blue, so I have to color this black. But now I can't color this black or blue. So, okay, well, I ran out of colors. I have to color this green. So it seems like the more cycles we have, the more colors we need, right? And it seems like if I have bigger and bigger cycles, so this is obviously...
Yeah, we can conclude immediately that if we want to, as long as we have no cycles, we're only restricted to having a chromatic number at most 2. If we want a bigger chromatic number, we need to admit cycles of some size.
Yes.
You're alluding to now odd cycles have this property that definitely can't color them.
Right. But more, even more, it also alludes to the fact that, or not, it's not a fact, it alludes to the conjecture that if your girth is really large, then your chromatic number is really low. And the reason this is true is, well, this isn't true. I keep doing that. The reason this seems to be true is because a graph of large girth is locally, it looks like a tree. Because what I can do is I can pick a vertex, play this game, and I'm guaranteed to have like about, let's say the girth is L, then I'm guaranteed to have about L over 2 layers before I run into any issues. So I can do this game until about L over 2. And I won't have any repeated vertices, because if I did, then I would find a cycle whose length is less than L. So locally, these things do look like trees. So that alludes to the fact that I can get away with coloring all those layers just using 2 colors, and I should be fine, right?
Yeah, and so like there's the background hidden assumption that chromaticity, the minimum chromatic number, is somehow related. It's somehow a local property of the graph.
Right. Exactly. Exactly. Yes. This is the assumption, and you can't be further from the truth when we say that. And it's been proven by Paul Erdős, one of the pioneers, like I said, of the probabilistic method, using guess which method. The probabilistic one. Yeah. Definitely not deterministic.
High probability of that being true.
Yes. Yeah. But you may be thinking, well, but didn't Boyun give us a constructive proof? And you said these things are, this method is really useful when you can't construct something. That's when you use it. How come? Well, first off, Boyun is a genius. You can't do what she does. But also, it took about over a decade after Paul Erdős's proof for the constructive proof to show up. And when it did, it was only for a very specific case of the general theorem that he was able to prove. So we will write down these theorems. I think I'll do at least this part. Should I keep doing blue, or should I do black and then go into blue?
Okay. We can see it just fine.
It's all good? Okay. So I'll keep this, whatever. So the first theorem is, this is the theorem that Boyin showed us a constructive proof for. There exists graphs, I should write triangle-free graphs such that the chromatic number of the graph is greater than k for all k, any k greater than 1. So if I pick an arbitrarily large k, I can construct a graph that's triangle-free that still needs that many colors before it can be properly colored. So this kind of almost breaks our assumption, right? For the 3 case, so it says that if the girth is greater than or equal to 4, then you know that our assumption doesn't work here. But Paul Erdős was able to prove something even stronger. I want to leave this for as long as possible. I'll try to work around this. And he says for all g and k greater than or equal to 1, there exists a graph G such that the girth of G is greater than G and the chromatic number of G is greater than K. There. So now it's obvious that what we thought isn't true. I can pick the girth to be as large as I want, and it doesn't really affect the chromatic number. I can still find counterexamples where I need a lot more colors, despite trying to do this algorithm. Erase this. So here's where the strength of the probabilistic method comes in. Like I said, this theorem is not much harder to prove than this theorem. They both use the probabilistic method. I'll be proving this one. And I actually highly encourage you to try to prove this one yourself after seeing the proof of the first one. And about a decade later, a construction that only proves this theorem came about, but we couldn't do anything better. So it is still a hard to construct idea. These counterexamples are still hard to construct, but the probabilistic method allows you to already prove the existence of such graphs. So we'll get into trying to prove this. How much time do I have? 40 minutes? Okay, then I think it's good. Yeah, I think we will get into the proof of this theorem, and this one I will leave it to you guys, because it is a series on the probabilistic method, which is like very known for being beautiful on the proof side, not on the result side. The results, they vary on in every field, but the proof methods themselves is what's like captivating in some sense. So I do want to like actually get into the nitty-gritty details of the proofs. So yeah, I'll try to prove this one by today. And to prove it, we only need, believe it or not, very simple tools. I'll write them down here. So a couple tools that we need. The first one is that the expected value of a random variable being less than or equal to t implies the probability that x is less than or equal to t is non-zero. So it's intuitive, right? The expected value is like some sort of it's a weighted average. It is a weighted average. So if all the probabilities are only greater than t, then the expected value, there's no way it was there, right? It should have been larger. You can try to prove this yourself.
The average is somehow sort of like a convex combination of the things you're averaging. And so if you're outside of the convex hole,
then how did you get there? Yeah, exactly. And the other tool we're going to use is Markov's inequality. This split down the middle sucks. What? Because it's in the middle of the, it's right in the middle. Yeah, I want to. Okay, Markov's inequality. Probability that x is greater than or equal to t is less than or equal to the expected value divided by t. This is another very intuitive notion, right? If you stray far enough away from the expected value, if you stray far enough, you should only find unexpected things because you strayed away from the expected thing, right? So if t is really large, then this side collapses to 0, so then your probability of finding anything above that is going to be low. I would highly recommend trying to prove these two as well. Actually, if we're going to honor the person that's responsible for this glass whiteboard chalk hybrid anomaly being in this room, I would say this is exercise 1, this is exercise 2, and we'll make this exercise 3. You can try these at home. Okay. And this is all we need. These are the only tools we're going to be using to prove our theorem. Everyone good on the definition? Okay. I'll leave it on the board just for, because someone showed up. I guess we'll start. Okay, I can. So let's start here. And we're going to start by selecting a random graph. On n vertices with such that for all the edges, for every edge, I guess. How should I notate this? Okay. Yeah, okay, so for all the edges, the probability that E is in your edge set is, well, we'll call it P first. That way it's easy. And P is equal to n to the negative 2/3. So what this means is I take n vertices and with probability n to the negative 2/3, I choose whether or not.
Yeah, when you're arranging over all edges, is that like all edges on the complete graph?
On the complete graph, yeah. I should. That's what I was trying to figure out what to say, yeah.
I was just asking because like maybe you could do it to just any other graph that's larger than it, perhaps. So.
That's larger than it. You could, but then like some of the probabilities would be, some of the probabilities would be 0 because some of the edges wouldn't make sense if it's larger than the complete graph. But yeah, so you take n vertices, and for any two possible edges, or any two possible, any two vertices, the possible edge has a probability of that to appear in your graph, right? So now you have a probability space. And where did I come up with this n to the negative 2/3? First off, I didn't. And the way you do is you basically work through the proof without assuming anything about P. And then at some point, you'll run into problems. And you try to fix those problems, go back and forth. At some point, you realize, well, that works. And that's how you come up with those numbers. I'm going to drink some water. I'm so dry. Any questions so far? Okay. How exactly were you?
Because the way it's phrased right now is like, yeah, take any edge that could exist on the complete graph of those vertices. I was just thinking, what if you were asking the same question, but from some graph that still lived on the same set of vertices, but contained all of the edges of your original graph, obviously, not necessarily the complete.
Oh, I see. So you take.
Now, obviously, the complete graph on a set of vertices is completely characterized, so you don't have to like do anything. There's no information.
Exactly. Yeah. You would have to start with the right graph, otherwise, and if you don't start with the right graph, you're not going to. Yeah. you're not going to find the thing that you want to find. And here, yeah, here you're guaranteed everything. So, okay, so we randomly select a graph, and what we want to find is the end goal should be that you want to bound your expectations of the number of well, okay, this wouldn't make sense until I say this part. So let's say that your graph is k colorable, or less than k colorable, like k minus 1, k minus 2. If that's true, then there should exist an independent set of size n over k. So if you have k colors and you're able to properly color the entire vertex set, then there should be some color that has n over k vertices, right, assigned to it, at least. And that must mean that those n over k vertices are independent of each other. There are no edges going between them, right? So essentially proving that a graph with, we're proving this theorem, so proving that a graph that's triangle free has a large chromatic number comes down to saying, well, there are no independent sets that are that big, right? So what we want to be counting is the number of independent sets in your graph. So let's call I the number of independent sets, meaning, again, vertices with no edges between them, of, we said the size was n over k, right? We want to count the number of independent sets of size n over k and prove that that has a low probability of happening. But, God, I really needed to drink more water. But for reasons you'll see later, actually, I'm going to add a 2 here, which doesn't change our result. If I'm just saying that even something smaller doesn't exist. So the big thing, you can forget about it, right? So that's what we want. And so I counts the number of independent sets. What we want to calculate is essentially the expected value of I. Then we can use these nice theorems, nice tools we have to bound the probability that these independent sets exist. And for this, we're going to use another essential tool, the linearity of expectation. We're going to call for some set. That's a subset of and choose. So for some collection of, it should be a, yeah, for some collection of n over 2k vertices, we say I sub s is the indicator, I'll just say, it's the indicator variable that tells you whether it's an independent set or not, and in essence, it's 1 if s is independent, and 0 otherwise. So the variable is 1 if s doesn't have any edges between them, it's 0 otherwise. By the linearity of expectation, the expectation of I is just equal to the expectation of the sum of these guys. Well, yeah, you know what the sum is over. Because every time that it's an independent set, you're adding 1, so you're actually just counting the number of independent sets here. So, right. And by the linearity of expectation, you can just move the summation sign outside. How far low can I go here? That's it? Okay. Okay, so we just need to sum all these expectations, right? Yeah. I also wrote the exercise on the wrong thing, sorry. Okay. Even though it's a joke, I have to commit to the bit. Okay, so let's calculate the expectation of just the indicator variable, which, as you know, if it's an indicator variable, it's just the probability that it happens, the probability that it's 1, which should be the probability that independent, which means none of the possible edges spawned. So for an edge to not spawn, it has to have probability 1 minus p, and the number of edges is n over 2k. I'll write this bigger. Over 2k, choose 2. Right, so every possible pairing of vertices gives you an edge. So this should be the probability that your set is independent. So if I take the sum, then how many sets do I have here? How many sets of size n over 2k can I produce from the vertices? I need to choose n over 2k from options of n, right? So n, choose n over 2k. Okay. So this is our expectation. So we have to find a way to bound this. Also, I should say, sorry, I should definitely say, this is only true for for x, a non-negative random variable. Okay, that's important. X has to be a non-negative random variable, and we're only going to be dealing with non-negative random variables because we're counting things. So okay, let's bound this thing. So obviously, if n choose n over 2k is finding the number of subsets of a certain size, of this size that I can pull from n, it has to be certainly less than if I just take all the subsets that I can produce using n, n objects. Okay. This part, 1 minus p, just as a side note, I'll just write it somewhere here. E to the negative x is greater than, oh, sorry.
Just enough the chair.
Yeah. Okay. I'll write it here. For all x. Okay. So we're going to use that inequality. We have 1 minus p here. We're going to turn that into e to the negative p. Okay. Let's see. Let's plug in our p here. That should be right. Something wrong? I'm missing a negative somewhere. Oh yeah, sorry. Oh God, Jesus. Okay, that negative doesn't go away. Times n over 2k, choose 2. Okay, I'm going to get rid of this. Okay, so now we have this. The expression for n over 2k choose 2 is just n over 2k times n over 2k minus 1 over 2, right? So if, well, we'll first write that. But if I take something, another polynomial in n over 2k, say, or just in n actually, say n to the 1 plus 5/5 or something. The leading term here is n squared, and the leading term there is something a little less than n squared, right? So this polynomial has to take over if I increase in n at some point. It has to take over the other one. So since it's in the denominator, notice this is also, that's where it is, okay. Notice the negative, since this exponent is in the denominator, if this polynomial grows, then the exponent decreases. So then the expression becomes larger, so we should have, oh Jesus, okay. Oh God. Sixth. And we can combine these. So then we should have, we can combine these, and we should have 1 plus 5/6 minus 2/3. That's like n to the 1/6 or something. Sorry, n to the 1 plus 1/6. Okay, sorry about the confusion. So this is what we have. And the point is that 2 to the n is going to be killed by this term at some point. If you keep increasing in n, you have e, you have something to the power of something a little greater than n. So it's going to be killed. So my point is, at some point, you're going to have this for sufficiently large n. If I keep increasing in n, the expected value should decrease and go less than 1/2 at some point, which is what we want. So remember that. Where do I write this? Okay. So that's our first fact. And now we can use the thing that I erased. We can use Markov's inequality. So if, or do we have to? No, we don't. We have to use the first moment, which is the first thing that we did. So if the expected value is less than 1/2, it implies the probability that you'll find x to be, the probability that you'll find x to be greater than or equal to 1/2 should be positive. So the point is, we use the first moment method, which is the first thing that I wrote, the first tool that I wrote down, to prove that the probability that the number of independent sets that you have being less than or equal to 1/2 is positive. So there are configurations where I have independent sets. No, there are configurations where the number of independent sets is just 0, because these are integer valued random variables, and being less than or equal to 1/2 is the same thing as saying it's 0. So that's the main fact. That's the first main fact. So I'll write that here. Okay, so the next thing we have to do is prove that the graph is triangle free, and then we'll be done. Let's do that. For this, let's calculate let's calculate another expected value. I guess I'll use x this time. X is the number of triangles. So we do the same thing. In order to define this, we define a random, what do you call it? An indicator variable. or yeah, I do have to. Okay, so indicator variable xs for some triangle t, some possible triangle t. T is a triangle, so it's 1 if t is a triangle. And 0 if not. Does that make sense so far? Okay. So, right. Again, we do the same trick. The expected value of the number of triangles is just equal to the sum of these guys. Someone tell me how to calculate the expected value of this, one of these guys. It should be the probability that T is a triangle. So you have 3 vertices, so I take 3 vertices. What's the probability that it does form a triangle in my graph? Using what we have. So all 3 edges have to be in my graph. And that means for each edge, the probability, we have the probability. So it should be probability of 1 times the probability of the other times the probability of the other. 3 edges, so 3. So it should be p cubed. That's for just one of them. Or independent. For one possible triangle, if it is a triangle, its expected value of the indicator variable is p cubed. So if we sum over all possible triangles, how many triangles should we have in the graph? Triangles. N choose 3. We should have n choose 3 triangles in our graph because, yeah, we have n vertices and we just want to pick 3. Yeah, 3 things. Okay, so let's bound this same trick. Well, this is like n times n minus 1 times n minus 2 over 3 factorial. I'll just make this n cubed over 6. P is over 3, but then you cube it, so it goes away. And you're left with n over 6. Okay, I should have time. Nice. N over 6. So this should be your expected value. So I think this time we do use Markov's inequality. So E x being less than or equal to n over 6. But we know that if we want the probability that x, don't ask me why I'm doing this right now, but you'll see very soon why we had to do this. The probability that x is greater than or equal to n over 2 is less than or equal to the expected value over n over 2. Remember, this is Markov's inequality. So the probability that if you stray far away enough, then the probability should lower. This is Markov's inequality. So they should be less than or equal to n over 6 divided by n over 2, which is 1/3. I think at this point we have a strict inequality, so we can just make this strict. What this says is that the probability that I'll find more than n over 2 triangles is really low. Not that I'd find any triangles, because they could still be triangles, but if there are only a few, is what we've proven. So we'll write the 2 facts down. Okay. I should probably write it differently, because we proved that the expected value actually goes lower than 1/2, so I can make this better. I can make this 1/2 as well. So this implies, so now if the number of independent sets being 0, if it has a probability greater than 1/2, then what do I want to say? Yeah, okay, good. So when you add up the probability that there are more than n over 2 triangles and the probability that there are any independent sets of size n over 2k, you get something that's less than 1. Because, well, this implies the probability that less than 1/2. So the probability that you'll find an independent set is small. So I add these two probabilities up, and I get the is less than 1/2 plus 1/3, which is less than or equal to 1. I'll erase all this. So okay, so what does this indicate? What does this prove the existence of? Right, exactly. This is, I think, technically called the union bound. It's basically taking the worst case scenario of something that could happen. So if you take the actual probability that you want I to be equal to 0, and you want x to be less than or equal to n over 2, then in your probability space, say 1/2 of it, 1/2 of your space has has some independent set in your space, and 1/3 of it has more triangles than n over 2. So the worst case scenario is if these two don't intersect, is if they're independent of each other. But we're still saying in the worst case scenario, there's some space left, which means there's a part where none of this happens. And that implies that we have a graph there exists a graph G such that the number of triangles is less than or equal to n over 2, and there does not exist an independent set of size n over 2k. I think this thing is running out. Okay, so we're really close. We got the independent set criteria that we wanted, but there's still some triangles. What can we do with those triangles? This is a really neat trick. It's a very obvious thing. Once you do it, you're like, oh, of course. So the reason that we picked n over 2k instead of just our n over k that we wanted is because what we're going to do this time is select, pick a vertex, bless you, from each triangle. Yeah, you pick one vertex from each triangle and just delete it. So how many vertices have you deleted at max? N over 2, right? You've deleted at most n over 2, so you have a new graph G whose vertex set is at least n over 2. It's still, first off, it's triangle free because you've deleted all the one vertex from every triangle, so there can't be any more triangles. Oh, this is your new graph. You picked all those vertices, you deleted them, you have a new graph now, right? Yeah, yeah. Good. Okay. So yes, your new graph. it has at least these many vertices, and it's triangle free, and it still meets our criteria that it has no independent sets of size n over 2k. And the reason now you understand why we did the 2 is because you actually wanted to delete this by the chromatic number. This is what you wanted to do, right? If your graph had n over 2 vertices, you would want there to be no n over 2k independent sets, right? And that's where the 2 came from. That's why you wanted to prove something even stronger. And this is the graph that you want. So as long as you let n grow to infinity, at some point you will find a graph using a random process that satisfies some looser constraints, and then you can take that graph, reduce it at max by half, and you'll get the graph that you want. So I think the proof it speaks for itself, because it's really, I mean, you saw the tools that we had to use. It was literally the first page of the notes that I showed you. It's like, and each, the proof for those tools is like a sentence each. But the power of it, you can see it across the border. I mean, this exact same technique is used in satisfiability proofs, mathematical logic, combinatorics, graph theory, even in algebra. I think hopefully at some point in the series I can get to something cool like that. But yeah, that's the end of what I wanted to say. Please do try to expand this case. This is obviously the triangle-free case. Try to expand it to it's not that difficult, as you can see. I mean, if you basically follow the outline of the proof and make a couple changes, you should be able to prove for any girth, which is what you want. You want to prove that Earth has nothing to do with how beautiful it is.